and question and answer session. And the listener would choose the most impact award at the last 5 minutes of each speaker. And you can use your phone to scan the code to vote. Now it's my great pleasure to introduce our first speaker, Mr. Hao Huang, who is a PhD student from Beijing Institute of Technology. He is interested in object recognition. His topic is automatic multi-vision reconstruction method of complicated tubes for industry assembly. Now let's welcome Mr. Huang. Okay. Mr. Huang, please start your presentation.
Thank you. Thank you, Saturady. Hello, everyone. My name is Huang Hao, and I'm from School of Mechanical Engineering, Beijing Institute of Technology. I'm from Digital Manufacturing Laboratory. The research interest of our group are 3D reconstruction, pattern recognition, and photogrammetry. It's my pleasure to be here to make this presentation. The topic of my presentation is automatic multi-vision reconstruction method of complicated tubes for industrial assembly. My presentation includes 5 parts. Firstly, I will introduce the background of tube inspection, and the tube mainly refer to those applied industry products. Then the algorithm will be generalized. And in the next part, I will describe the implementation process in detail. The last 2 parts are related to the experiments and discussion. First, the introduction part. As is shown in the picture, the complex tubes are used in agri-space vehicles and electromechanical products for transforming material and energy. The tube assembly is critical to products' reliability, performance, and life cycle, and therefore, Merida process the tubes and fix any geometry errors to satisfy the assembly requirement is important. The reliability of tube assembly is directly affected by the machining quality of the tubes. As is shown in the picture, the tube is bent by the CNC machine, and we can find that the tube configuration gives away to surrounding equipment, and the joint pose includes the distance and the relative direction of the head and end. So tube measurement ensures production quality and enables reliable and stress-free assembly. At present, the method used for tube measurements in the literatures and in applications can be divided into 2 broad categories: contact and no-contact methods. The contact methods consist of mechanical gauges and 3 coordinate measuring machine, and the non-contact methods include the laser scanning and the machine vision. The first 3 methods are time-consuming for tube with a complex shape and depend on human interaction heavily. Generally, the machine vision-based method is high efficiency, operate easily, and applicability generally. At present, the tube measurement methods based on the machine vision mainly include the following parts. The first kind of methods is to attach mark points to the tube surface, catching the landmarks from image to reconstruct the tube model. However, these methods are complicated and inefficient. The second methods are based on the 3D geometry. Tubes are composed of line segment and arc segments. Therefore, these methods determine the position and orientation of these features to complete the measurements. But these methods heavily depend on the geometry size and cannot be used to complex tube. Next methods are based on the Harris points. Through reconstructing the Harris points, 3D model can be completed, but the accuracy point often affects the precision. Joint measurement includes two kinds of methods based on the viewpoint ball and the target points. One needs to extract the edge and match the edge. The other needs human interaction, which is time-consuming. Besides, there are still many problems to be solved. The general reconstruction process can be separated into 3 steps: key point extraction, matching, and reconstruction. Extraction and matching determine the results of reconstruction. A significant question in tube inspection is how to accomplish the recognition and segmentation of line and arc segments of tubes, which can later be applied to calculate machining parameters. However, due to the absence of a fine invariance in line and arc segments, especially when they are short, it's impossible to recognize this characteristic in images, just like in this picture. As is tube surface lack of texture and other characteristics which can provide strong clues to the 3D shapes, it can be difficult to match common details between images, thus hindering reconstruction. The necessity to process the tube surface as light reflection greatly affects the application and reduce measurement efficiency. Finally, the complex tubes with large size variation result in occlusion issue. So it's necessary to develop a tube measurement system to provide new solutions for tube measurement in actual production. Next part, I will give an algorithm overview. We propose a method to reconstruct the tube by calculating the 3D coordinates of the bending points and the endpoints. The algorithm flowchart is as follows. Our method consists of 3 parts, including tube detection, initial model, and tube model reconstruction. At first, backlight was used to minimize the influence of reflection from tube's surface. As multi-cameras are calibrated, the tube images can be acquired. The tubes are segmented. Finally, the tube edges are extracted. The second part is initial model, aiming to determine the initial point in each image. The reference image and the start location in it are determined to define the origin of the reconstruction. Then, the epipolar line is used to determine the start locations in other images. As is shown in this picture, small cylinders are reconstructed along direction 1 and direction 2 to the ends of the tube to build the initial model. The last section is tube model reconstruction. We aim to determine the key points, including the bending points and endpoints, and these points can be used to reconstruct the tubes. Now, I will introduce the reconstruction method in detail. In order to promise the measurement precision, we need to calibrate the cameras, including the intrinsic and extrinsic parameters. The principle is to establish the correlation between spatial points and pixel points using the encode points. As shown in the picture, each encode point can be determined using the spatial encode value. For example, spatial point 100 corresponds to image point 100, and the initial camera parameters can be determined using the relationship. After obtaining the initial parameters, a spatial point can be projected into the image, and we optimize the camera parameters by optimizing the distance of the projecting points and the image points to calculate the camera calibration. Then we can acquire the tube images from different views and extract the pixel edge points to ensure the inspection accuracy using Canning operator. The backlight minimizes the reflection and forms a strong contrast between the tube and the background, which contributes to the extraction. The second part is initial model, aiming to determine the start location. The start location of the reconstruction can be at random position rather than the end point. Firstly, extract the skeleton of the tube region and connect the 2 pixels of the skeleton. The perpendicular bisector of line L intersects the tube in the image, and the intersection point is the start location in reference image. We can determine the point P1 and P2, then obtain coordinate in world coordinate system. Then project the points to other images. Finally, use the trifocal tensor 0 to solve the matching ambiguity. Now, we determine the start locations in all images. Then we start to reconstruct the tube using small cylinder. Reconstruction of the small cylinders is a saluted-based method. Firstly, we determine the reconstruction direction from the image. The reconstruction principle is as shown in this picture. Starting from the start position in all images, pick a small section along direction 1 as the pyramid tip. Shorter cylinders affect the efficiency of the calculation, and the longer cylinders affect the recognition of short arcs. Our proposal is 4 mm long. Build a small cylinder in world coordinate system and match the edge points in the image to the border of the cylinders to determine the pose of the small cylinders. Reconstruct all the small cylinders with this method in direction 1 and direction 2. All of the small cylinders comprise the initial model of the tube. The small cylinders are reconstructed by matching the border of the small cylinders with the edge points in the image. In the implementation process, due to the radius of the small cylinder is equal to the tube's radius. Therefore, the center line is used to represent the small cylinder, a projection center O1 or O2, and an edging point from a line LG. Ideally, the distance between the center line and the LG is equal to the radius, so the center line can be determined by minimizing this formula. As the cameras are in different locations, and after the occlusion judgment, the occluded part of the tube can be reconstructed by other no-occluded images. So the occlusion will not affect the results. Initial model reconstruction, that is multi-small cylinders reconstruction, now has been completed after about 4 steps. Principle of feature recognition. The cylinder is a line segment, so the matching errors with the line segment and the arc segment are different in the image. As shown in this picture, for example, we can find that 51 to 69 can determine the first arc, and the other 2 arcs can also be determined. Besides, the length of cylinder is 4 mm, not only ensures the correct identification of features, but also ensures the accuracy and speed of reconstruction. The measurement range is 20 degrees to 117 degrees. After fitting all of the line segments of the tube, the common vertical line of 2 adjacent line segments is calculated. The center point of the common vertical line is a bundle point in the tube. Based on that, we can obtain all the bending points. Finally, we project the first cylinder to the image to get the edge and optimize the length of the line segment to get the endpoints. After getting bending points and endpoints, the whole tube can be calculated accurately. Next, we'll verify the precision and reliability of the proposed algorithm by experiments. The hardware is composed of a backlight source, cameras, and a computer. This platform uses 16 cameras in total, arranged as shown in this picture. The model reconstructed by the CMM was taken as the standard model of a tube, and the precision of the CMM was 0.003 mm. The performance of the proposed tube measurement method is evaluated by calculating the CJK value. The process of experiments is as follows. We first construct the reference model using CMM and make the experimental tube model 50 times using our algorithm. Finally, compare two models and we can obtain the CDK value. The acceptance criteria CDK is 1.33, and the higher value, the performance better. According to the results, we can find that our mean CDK is 1.83 greater than the acceptance criterion of 1.33, indicating that 6,210 error results will occur in 1 million reconstructions. Therefore, the qualification rate is 99.9937%. The proposed algorithm showed good performance. Besides, we verify other tubes with different characteristics. Results show that our algorithm is accurate and visible. The last part is discussion. We propose a multivariate-based reconstruction method for tube inspection. The method regards small cylinders as the primitives to reconstruct the tube, and we use the matching error to recognize the line and arc segments. Also, multi-camera solve the occlusion issue and improve the reconstruction precision. In the future, we will make the backlight illumination it's easier to extract the subpixel edges, and also we will optimize the number and the distribution of the cameras. That's all. Thank you. Okay, my presentation is over.
Okay. Thank you very much. It's a very interesting presentation. And now we have enough time for the questions. So are there any questions? Okay, are there any questions? So I think it's a very interesting research to reconstruction the tube. Okay, if there are no questions, I think we also can communication after the conference. Okay, now it's my great
Sorry,
pleasure.
I think there is one.
Okay.
Sorry, but there is one in the chatting box from Zheng Yi. So this is one selected question. Can you see that?
Oh, okay. I see that. Mr.
Dr.
Huang. Oh, okay. Mr. Huang, can you talk more about the evolution?
Okay. And we use the standard model reconstructed by the CMM, and the evolution criteria is the CJK value. It's usually used to evaluate the repeatability and deviation of a measurement system. Along and vertical to the tube at the end points and at the target points, the model has 10 sets deviations, and we use these deviations to evaluate our model to between the standard model and our reconstruction model.
Mr. Huang, is there is another question? Can you detail the process of calibration? Can you detail the process of calibration? Dr. Huang.
Okay. The calibration of the process of the calibration. The calibration principle is establish the correlation between the spatial points and pixel points using the encoded points. We use the bundle adjustment and the special point, the coordinate in special point we can obtain, and using the just like I described in this presentation, for example, the spatial point 1000 corresponds to the image point 1000, and the initial camera parameters can be determined using the relationship. We minimize the formula, then the extrinsic and intrinsic the parameters of the cameras can be calibrated. Okay.
Okay, another question. How to determine the camera pose?
The camera pose is determined using after we calibrating the cameras. It can be obtained by the calibrating. The PNP can get the initial parameters of the camera, and we use the bundle adjustment to optimize the camera parameters. Can I solve your question?
Okay. Thank you very much for Mr. Huang. I think we should start the next speakers. Now, it's my great pleasure to introduce our next speaker, Mr. Tianxin Huang. He is from Zhejiang University. His topic is 3D point cloud geometry compression on deep learning. Don't forget to vote the most impact award at the last 5 minutes of the presentation. Okay, now let's welcome Mr. Huang. Mr. Huang, please start your presentation. Thank you.
Okay. So could you hear me? Hello?
Yes.
Could you hear me?
Yes, we can hear you.
Okay.
Yes, your voice is pretty clear.
Okay, thank you. So hello everyone. My name is Huang Tianxin from Zhejiang University, the April Lab. And today I'm glad and it's my great honor here to share a presentation on my topic, the three-dimensional point cloud geometry compression based on deep learning. So now let's begin with a simple introduction about the point cloud and the point cloud compression. First is the point cloud sensors. And the point cloud is very common use data format now. There are multiple kinds of sensors to acquire point cloud data, including LiDAR, RGB camera, and stereo camera. LiDAR is often used in outdoor scenes, and RGB camera is often used in indoor close-up scenes. And stereo camera measures steps indirectly by the difference between two cameras on it, and its accuracy is related with distance between them. So it is often used in close-up scenes also. So where point cloud use? Point cloud as a common description to three-dimensional space. It is easier to acquire than other three-dimensional format data, such as voxel or mesh models. So it is widely used in applications relying on three-dimensional data, such as the automatic driving and augmented reality and virtual reality, so-called AR and VR. In automatic driving, point cloud is used to draw maps and observe surroundings to navigate the operation of vehicles. And in augmented reality or virtual reality, three-dimensional models need to be transferred and displayed in user's terminal. So why do we need compression? I think it is because we are facing the challenge of big data. Point cloud compression is important because it can largely reduce burden during transferring and saving after they are acquired from sensors. Sensors such as the HDL64 can acquire up to 20 to 100,000 points a second. So for AR and VR, high resolution models are also needed. They contain large numbers of points, so it will be hard to transmit or save so much points directly. Good compression algorithms can improve the transmission and saving efficiency largely. So the next question is how to compress point clouds. There are two main ideas to compress raw point clouds data at this time. And one assumes that there are lots of redundant points in raw models. It tries to remove redundant points from raw points, only keeping key points. And there are multiple key points extraction algorithms such as ISS or SIFT, and it need to be chosen according to real condition or downstream tasks. And it will always cause information loss because it is exactly a kind of downsampling algorithm. And the other idea is to encode raw point clouds by some predefined rules, such as the Oct.17. And it will keep more information and adaptive for multiple downstream tasks. So we concentrate on encoding method in our work. So compression by encoding, it is to transform raw data into binary stream or memory saving format. It is more reasonable and effective because data is actually binary format in memory or during transmission. And by designing reasonable encoding rule, the information entropy after encoding can be largely reduced. So compression by encoding can also be combined with other methods together to improve the compression effect. They are all compatible. Now I'll give a simple introduction about a common used point cloud encoding and compression algorithm, the Oct.17 compression. So it is like this. And Oct.17 encodes point cloud by recursively partitioning the input space into equal octants and storing occupancy in a tree structure. Each intermediate node of the Oct.17 contains an 8-bit symbol to store the occupancy of its 8 child. So with each bit corresponding to a specific child, empty or not empty, the symbol for empty is 0 and not empty is 1 here. So we can see that the second level of Oct.17 can be encoded as 010000010 in this way. And it is obvious that resolution will greatly improve as the train depth increases. A leaf point is quantized as center of its center coordinate. Then the model can be encoded by breadth first traversal or depth first traversal in this way. So we can see that existing point clouds compression algorithms are basic encoding algorithms. So what if we combine it with deep learning? What if we try to learn an encoding rule directly from the data? And this is exactly the core of our work. So here come our methodology. Our basic framework is like this. Our work consists of two parts: a new hierarchical autoencoder to do network compression and decompression, and a sparse coding layer to improve compression ratio. which is lossless, and the compressed code word is transferred from sender to receiver. Encoder and decoder will be saved separately by sender and receiver to finish the whole process. And in our network, a multi-scale feature extraction structure, same as that used in PointNet++, is used in our encoder. Then the code word is compressed again by sparse coding. Compressed code word is decoded and fed into the network decoder. The decoder generalizes an initial feature matrix by deconvolution first. Then the decompression layer expands the feature matrix and generalizes point clouds of different resolutions. There are 3 different resolution outputs in our decoder, and the final loss is weighted sum of losses for the 3 outputs. So we can see that our decompression layer is the key architecture of our decoder, and it is used to expand raw local feature matrix to 4 times larger. It consists of 2 deconvolution layers in different dimensions and 1 convolution layer in another dimension. The local deconvolution layer is the first. It transforms raw feature into local feature spaces composed of multiple feature vectors. The local extension layer divides the local feature spaces into 4 subspaces. Then the subspaces are combined again by a space combination layer, also known as a convolution layer. So this is our decompression layer. And another very important work is our loss function. The most common loss metric for point cloud learning and reconstruction is the transfer distance. And in our work, we use multi-scale loss to evaluate loss in different scales. We evaluate loss not only by global shape, but also by neighbors around n sampled centers with radius r. We combine simple transfer distance and multi-scale loss to make up the multi-scale CD loss upside. So obviously it can capture the shape very well because it combines local and global differences together. Besides, to improve compression ratio, we need to improve the sparsity of the code word extracted. So we add an L1 regularization of code word to the multi-scale loss. And finally, we use sparse multi-scale CD to train our network. And multi-scale CD is the test metric for reconstruction loss. So the next I want to tell is the sparse coding. Sparse coding, as I said just now, it is simple and used with sparse constraint in loss function together to improve the compression ratio further. It means to record positions of non-zeros in code word by encoding these positions into binary format. And in this way, a long sparse array can be described with a short non-zero array and a short position record array. If we describe memory of single number with length and percentage of non-zeros with s, and the memory of words after sparse coding will be like in Formula 1. And the condition that sparse coding works can be shown in Formula 2. We can get Formula 3 according to Formula 1 and 2. And from Formula 3, we can see that sparse coding can work if there are more than 1 zero in raw words. It means it can always work. Compression ratio will be higher, while raw words is sparser according to Formula 1. And this is exactly the reason we add L1 regulation to multi-scale CD loss just now. And our work is based on ShapeNet part dataset containing 16 categories from the whole ShapeNet dataset. Each model consists of 2,048 points sampled on the triangles from corresponding mesh models. The formats are unordered coordinates. So this is our methodology. And The next is our experiment. To compare the generation ability visually, we choose a few models from dataset to evaluate our work. Fortinet and fully connected network are the most common point cloud representation learning networks. And the result of our work is shown in the red table. Fragile shapes are highlighted with red circles in the picture. And from the result, we can see that although Fortinet creates a smoother surface, it cannot reconstruct the discontinuous shape or non-manifold surface well due to its folding operation transforming two-dimensional planes to three-dimensional surfaces. And the fully connected autoencoder improves that point, but it may build rougher surfaces. Our network can reconstruct the discontinuous shape smoothly, better than both of them. And to choose reasonable metric, we test different functions on our network, and we find that the multi-scale CD we mentioned just now has the best reconstruction effect. So we think it means multi-scale CD can capture point cloud shape the best. So we use multi-scale CD as our reconstruction loss metric. And from the table in the right upside, and we can see that our work performs better than fully connected network and folding net on this metric. So next, to compare our compression ability, we compare our work with PCL and Jekyll algorithms on test split of our dataset. And the results are acquired when improve compression ratio as high as possible for PCL and Jekyll. Reconstruction loss is all evaluated with multi-scale CD mentioned just now, and the compression ratio is evaluated with bits per point. It means mean memory taken by each point after compression, and smaller bits per point means higher compression ratio. 16 and 32 in the left picture means to save code word with 16 bits format or 32 bits format. And the result shows that our work can reach much higher compression ratio while keeping a smaller reconstruction loss. But it is weak in time and memory cost due to the framework and program language limit because PCL and Jekyll are implemented on C program, and it is quicker than our Python-based program. Besides, TensorFlow may keep all intermediate matrices in the memory during the forward propagation process. So it also leads to memory cost. And so simplifying network and replacing more operation in TensorFlow with C program may improve the efficiency and reduce our memory load. So this is our experiment, and now I want to make a conclusion and discussion for our work. In this work, we make an attempt to compress three-dimensional point cloud by deep learning. And our algorithm can support parallel processing multiple models by GPU simultaneously. And it can reach higher compression ratio while keeping tolerable loss. It is also compatible with other algorithms because feature acquired can be used for other tasks, such as recognition or segmentation. But there are also some disadvantages and more works to do in the future. First, robustness of deep learning-based methods needs to be improved. It has difficulty dealing with point clouds with different densities and very complex or discontinuous shapes. Besides, compression ratio is fixed once training ended in our work. So alternative compression ratios should be provided to satisfy different occasions in real condition. And more information such as normal vectors or colors should also be taken into consideration because they are also important sometimes. And Memory and time cost during compression is also too high in our work at this time, and more work will be done to reduce it in our future work. And so that's all. Thank you. Thank you for your attention, and I wish you have a good day. So, any more questions?
Okay, thank you very much. It's a very interesting presentation. Now we have about 3 minutes left for questions. So are there any questions? Okay, I see one. Will your model works on multi-object senses, Mr. Huang?
Okay. Okay. For this version, our model is not work very well on multi-object scenes. But if you want to know about the multi-object scenes, you can just waiting for our later or new work. We will try to solve these problems in our next work. So that's this.
Okay, thank you. Is there any other questions? Okay. Are there any other questions? No more. Okay, thank you very much, Mr. Wang.
Okay, thank you.
Okay, now it's my great pleasure to introduce our next speaker, Zeman Shao. He is a PhD student in Purdue University. His topic is single view reconstruction for food portion estimation. Okay, also don't forget to vote the most impact award at the last 5 minutes of the presentation. Now let's welcome Mr. Shaw. Mr. Shaw, please start your presentation. Thank you.
Thank you for the introduction. Hi, my name is Zeman Shao. I am a PhD student from Video and Image Processing Laboratory, School of Electrical and Computer Engineering, Purdue University. Today, my topic is about single view reconstruction for food portion estimation. So I'll go through about the motivation and overview of my topic, and I'll introduce two methods of single view portion estimation. One is based on the geometric models. Another one is about learning image to energy mapping using the generative adversary networks. And in the last, I'll introduce the conclusion of our current work and talk about the future work. So recently, there's a report based on a white paper written by the Federal Nutrition Research Advisory Group called for strengthening national nutrition research through coordinated federal research efforts. So in this report, the states that there are about 46% of adults and 56% of children in the US have an overall poor quality diet. However, the US healthcare spending has nearly tripled from 1979 to 2018, from 6.9% to 17.7% of the GDP. So therefore, adverse health consequences of a poor diet are well known. However, assessing dietary intake with high accuracy remains a major challenge. Conventional methods of self-report dietary assessment include a food report for which a participant records all consumed foods and beverages along with any detail and portion size. Food frequency questionnaires list a variety of foods for when the researcher is interested in and how often the participant consume them. So the current gold standard in dietary assessment is a 24-hour record. For this method, participants are typically and the interviewers uses a series of questions and participants remember everything last P4. So the Shazam is an app for music identification, which also provides some functionalities such as singing songs, providing some additional information such as the title, the artist, and the album of the songs, and so on. So our goal is to develop a system which is like a Shazam for food, using a mobile device that will provide an accurate account of daily food and nutrient intake from a single image. So we built our technology assisted dietary assessment project called TADA project for more than a decade. If you want to learn more about the project, you can visit our website here. And deployed on more than 30 real-life user studies. The participants' age is from baby to the elders, and all the range of image collection days are from 1 to 58 days. And all studies are control fading and community dwelling. In total, there are more than 2,500 participants used our TADA system, and in total, there are around 72,000 images captured by our TADA system. So thanks to this large amount real life study image, we can build and develop our method based on it. So there are also some existing methods, include the one based on the 3D range finding, using the techniques such as structure light, and those based on the multiple images and videos using stereo view vision techniques. The structure light requires significantly modified mobile devices. Therefore, not all phone has rear facing depth sensor. For the taking image multiple view of the eating scene, it requires extra user effort. In addition, multiple view does not guarantee good reconstruction because the angle differences is too large and the scene has been changed between taken different images. Also, there are two another existing methods for food portion estimation. The ASVA group proposed to convert the food portion estimation into serving size classification. However, they didn't indicate the proper criteria designing serving size. And also, each food item will not only have finite number of food energy, which is not correct. And another group called Mayer's group, they also introduced the use of voxel representation for the eating scene. The voxel representation is obtained using the predicted depth map of the eating scene. The food volume can then be estimated. However, no validation results on food energy has been reported because the food volume to food weight still requires the food density. And also, there's no follow-up work ever since the 2015. So therefore, we introduced our method, the single view portion estimation based on the geometric models. So both in this method, we assume that food atoms in an image have been classified and associated with each food item has been obtained. Then camera calibration is applied to the original RGB image, and the volume is estimated by the feature point extraction and shape template matching. Once the food volume has been estimated from the image, then the energy of food consumed can be estimated based on the nutrient information. We use a black and white checkerboard as our feature marker the checkerboard is required to be placed in the scene to estimate the camera intrinsic and extrinsic parameters. Furthermore, fiducial marker can also be served as a size reference for objects included in the scene. In this work, we highlight the cylinder model because there are many foods are served in containers, and the most commonly used containers that have significant 3D structure each either have the cylinder-like shapes or can be approximated to the cylinders. The cylinder's volume can be obtained if the radius and height are known. As a result, instead of complete 3D reconstruction, we would like to focus on estimating the essential parameters to represent radius and height. Points of interest are selected accordingly to carry the sufficient information required. Thus, we will focus on the estimation of points of interest. Other than the cylinder model, we use prism model, which is an area-based method for foods that have non-rigid shapes or no significant 3D structure, such as those laid on the plate, like the scrambled egg in this example. We assume the head is the same for entire horizontal cross-section. As it is an area-based method, we can use a plate size if we know as a size reference for the estimation of the food portion size. So for the food data we tested, we have ground truth information for food labels, segmentation masks, portion size in weight, and energy for each piece of food. And we have a total of 19 types of food, and we use cylinder models for 9 types of food and the prism model for the rest 10 types of food. We estimate the weight for each piece of food and the total energy contained in each eating scene image. So here's our experimental results. As you can see in this figure, most food items have a 15% error or less, which are the ratio shown in the figure from 0.85 to 1.15. Out of the 19 food type, only 3 types of food, the 14, the lettuce, the French dressing, 16, and the 13 ketchup, have estimated errors larger than 15%. Given the low energy density of lettuce, the error represents approximately 2 additional kilocalories. For the ketchup and the French dressing, the errors generated are due to the head estimated by the cylinder model. So, however, there's still some challenges of geometric model-based methods because it requires correct food labels and segmentation mask. It's sensitive to errors in camera calibration and propagated from food classification and segmentation. So, and also we need correct food density to compute the energy. And so we have a question. So can we directly convert the food image, the RGB image, to the food energy directly? Therefore, we introduced another deep learning-based method. We introduced this method called learning image to energy mappings using generative adversarial network. So in this method, our goal is to learn the mappings of the food images to the food energy distribution using the generative models. So the food energy distribution, here's an example. It represents the relative spatial amount or the weight of food energy at the corresponding pixel location. Therefore, food distribution not only provide the insight on where the food items are located in the scene image, but also reflects the weights of energy in different food regions. So as for the generative model, we use a generative generative adversary network, the GAN, to generate the energy distribution map. So for the common GAN, there's two parts. One is a generator, generator G, which generates the fake data, and also another model called discriminator D, which is trying to distinguish between the real data and the fake data. So as for the conditional GAN, the CGANs attempts to learn the mapping from a random noise Z to a target Y based on the observation X. So the objective for conditional GAN can be expressed as a below formula. Therefore, the conditional GAN architecture is a natural fit for our image to energy mapping task, because we want to predict the energy distribution map based on a food image, the RGB image. So in order to train the conditional GAN, we need paired food image and energy distribution image. However, there's no publicly available dataset contains enough information for training the conditional GAN. Therefore, we created our own paired image dataset from the food images collected from the real-life dietary study. By synthesizing the energy distribution map based on the ground truth information below, such as the original RGB food images, the ground truth food label, segmentation mask, and the food energy. Below, here's an example how we generate the corresponding energy distribution image. The chip region is mapped to energy distribution image region. The Fisher marker is also used for image rectification. So for predicting the energy distribution image, we use 1,875 image pairs to train the conditional GAN, and we evaluate the energy estimation error rate at the below formula. And below it, here's an example of the original eating occasion image and it's a associated ground truth energy distribution map and the energy distribution image estimated by the conditional GAN. So we compare the energy estimation error by using two different generative models, the encoder and the encoder, decoder, and the unite. So at the epoch 200, using the UNIT as a generative model, the energy estimation error rates are 10.89% if we use the L1 creator region, and 12.67% using L2 creator region. So since we are able to estimate the energy distribution image for each RGB eating occasion image, our goal is to estimate the full energy, a numerical value based on the estimated energy distribution. Therefore, we train a convolutional neural network, the CNN, to estimate the energy from energy distribution image. The ground truth of full energy values in each image are provided by the registered datatins in a free living study. Here's the architecture of the regression model we use to predict food energy based on the energy distribution image. We added an additional fully connected layer to convert the VGG16 network output to 1x1 dimension and energy value. We also use the pre-trained weights on ImageNet for the VGG16 architecture and train the network for food energy value estimation based on the energy distribution image. So here's our experimental design. We use 1,318 location images from a free living dietary study with ground truth energy. And also we use 1,043 of them for training the model, and 347 of them for testing the accuracy of the estimated energy. Here's our energy estimation results. We compare the estimated food energy from energy distribution image to the ground truth food energy. As you can see from this figure, most of the results are near to the zero error. And the average absolute error of energy estimation is 209 kilocalories. So our in this work, we develop a single view food portion estimation technique using both geometry models and deep learning based approaches. We believe if we collect more 3D information from consumer depth sensor on mobile devices, we will further improve the accuracy of food portion estimation with, without adding user burden for real-world application. That's all I want to talk. I'm ready to answer your questions.
Okay, thank you very much. Very interesting research. Okay, are there any questions?
I have one question.
Okay.
It's about your final estimation result. So you had an experiment, right?
Yes.
I saw the error distribution result, which is pretty good. I'm also curious about if you have accumulated probability. For example, with like 95% confidence, what's the accumulated error you can expect?
I'm not sure the exactly the propagated error rate in the final estimation.
No, not propagated. I mean accumulated. So you have probability density, right? It's like probability density. It's not accumulated, but as a user, I'm curious about. So with 95% confidence, what's the error of this estimation algorithm?
Do you mean the 95 confidence for the estimated
error? Yes.
Food energy distribution map?
Yes.
So
do you have the result, or
do you mean the results for the accumulated error from the energy distribution map to the final estimated
yes, so it's pretty simple. You just add them up and you can have the result.
We don't have exactly the accumulated error compared to the final energy value. So cause the you can see in some eating scene, there's some food is hidden in another ones.
I see. You're right.
So so this grape is in a bowl, so we can only see the top of this grape. Therefore, the estimated distribution map is not accurate because we cannot predict the headed things. So it's obviously that this error will be accumulated to the final value in estimation.
Okay. Thank you very much.
Did I answer your question? Yeah.
Yes. Yes.
Okay, are there any other questions? Okay, I think very excellent Q&A sections. Now we have 10 minutes break. And we will start at 11:15. Thank you.
Thank you very much. Hello. Now, let's finish the coffee break. And let's welcome our first speaker in the second half, Mr. Guangming Wang. And Mr. Guangming Wang received the BS. You're in the group, right? Okay. Mr. Guangming Wang is a PhD candidate in Shanghai Jiao Tong University. His research interests include SLAM and computer vision. And today it's my great pleasure to introduce him and and looking forward to his presentation with a topic on supervised learning of depth, optical flow, and pose with occlusion from 3D geometry. And please remember to vote if you like this presentation, because after 15 minutes of presentation, a QR code will appear, but not in the meeting room. Instead, it's on YouTube or Bilibili, and scan the QR code to vote for the most impact board. And Mr. Guangming Wang?
Yeah.
Okay, you can start your presentation.
Okay.
Okay, I need several minutes to terminate my presentation.
Okay.
Okay, now you can start your presentation.
Can you see my PPT?
Yes. Yes.
Okay. Hello everyone. My name is Guangming Wang, and I'm from the Shanghai Jiao Tong University. My topic is the unsupervised learning of depth optical flow and pose with occlusion from 3D geometry. My topic includes the 5 parts: motivation, written work, method, experiments, and conclusion. The part 1. In the field of mobile robots and autonomous driving, the the visual time that is a key technology that for the decision making and the transaction planning. But there are some prompts for the traditional methods, like this. The molecular is needed to be initialized, and the feature-based wisdom faces some problems such as loss of matching features in dynamic environments, or sometimes few features. And our task is to conduct the unsupervised learning of depth optical flow and motion from molecular video. Related work. Our work is inspired by this work. For the first time, Zhou et al. Conduct the first unsupervised joint estimation of depth and motion from just molecular video. In their system, they have 3 images to input the system. The IT image and the depth network can estimate the depth of this image, and then he can get the point clouds of the IT image. And then the point clouds are projected to the consecutive frame, like IT-1. Use the pose. The pose is estimated by a pose network. Then the system uses the matching between the pixels in IT image and the IT-1 image. Use the matching relationship. The system can train the depth network and the post network. Our method is to estimate 3 masks to filter the occurring regions in the unsupervised of depth and pose, so we can filter some outliers that these pixels may don't satisfy the matching relationship. First, we use the consecutive true frame from molecular videos as the input. Then the depth and angle motion can be estimated by the depth network and pose network. Then we contracted the images based on the depth and angle motion. At the same time, we can obtain several masks for occurrence, like the black mask, overlap mask, and edge mask. Finally, we calculate the losses. We use the image contraction loss, the structure similarity loss, and the common smoothness loss. So we introduce the mask in details. The overlap mask on the project image. Before we introduce the overlap mask, we needed to introduce the linear interpolation mechanism that is used in image reconstruction. In the figure 2, for 1 pixel in the active image, when its depth is estimated, this point can be projected to the 3D. Then we can use the camera model to project this point in 3D to the 2D in T-1. But this point may be projected to a position like in figure 2, in not just in a integrate the position. This time, we use the 4 nearest pixels to interpolate the pixels in the reconstructed image, the T hat. In the process, maybe there are 2 points that to project a similar a pixel position, like the figure 3. When the camera at T frame can see the SCR, and the camera at T-1 frame cannot see the SCR. When the depth of T frame can be estimated, we can get a point cloud of STL and the front of the car. But when we projected the point cloud of SCL and the front of the car to the 2D at the T-1 frame, the front point cloud will be occluded. The SCL will be occluded by the front of the car. So, in this time, we need to filter the far pixels, like the figure 4. Then, but this cannot solve our condition. Like in figure 5, the SCR can be seen at T-1, but the SCR cannot be seen at T frame. But when we project the pixels in S1 L to the T frame, the error cannot be occluded by any pixels because these pixels can also not be seen by the T-1 frame. But we can solve this problem by project the pixels at T frame to the T-1. The pixels in SUR cannot be seen at T frame. So when the pixels at T frame are projected to the at T-1, there will be four, like the yellow points that they have no matched pixels. So these pixels should be masked. Then we expand our our method to the optical flow estimation. These are our occlusion mask, and we expand this by using this mask to the unsupervised learning of optical flow. We also use the depth pulse flow to supervise the optical flow in the occlusion error because the original losses for optical flow cannot constrain the training of optical flow. We also propose a maximum normalization to prevent the decreasing of inverse depth value in the training process. We also use a less-semi mask to filter the outliers after the occlusion mask to further filter the outliers pixels. Then the experiment. You can see in table 1, our results are better and it works. And the camera pulse estimation results and the optical flow estimation results. We also conduct the obliteration study on optical flow estimation. We can see that our occlusion mask, our less-semi mask, and the consistent loss can improve the results. Then there are some more visualization. For the image on the left, the first is input image, then the difference image between raw image and reconstructed image. The occlusion mask can filter the occluded error, and then the less-semi mask can filter the outliers again. Then the right image is about our maximum normalization. When we use the mean normalization, there will be a decreasing for the inverse depth. And when we use our maximum normalization, the training can be trained for longer times. The conclusion. In this in our work, the overlap mask and the black mask on the project image and the target image are designed to solve the pixel mismatch problem. The mismatched pixels are filtered to make the backpropagation more accurate, and the less-semi mask is added to further filter the outlier pixels. And an inverse depth minimum normalization method is proposed for the smoothness loss to prevent the problems of decreasing inverse depth values during training. We also propose a consistent loss that is use our the depth pulse depth pulse flow to supervise the optical flow in the occluded region. And our superiority is demonstrated on KHTI dataset and Cityscape dataset. The future work, maybe we can find more robust laws for the photometric change between the consecutive sensitive frames and to handle dynamic objects in a more accurate method. Yeah, that's and our source code is published on the GitHub. Thank you for your attention. That's all.
Thank you very much. And I have a question.
Yeah.
It's about benchmark and comparison with other methods in your experiment.
Yeah.
So the font size is quite small. I think this is from your paper, right? From your most recent paper, Transaction Intelligent Transportation Systems, right?
Yeah.
Okay, so do you have any like visualization or anything that better explains the advantage of the proposed method over the conventional methods?
Can you see this PPT? You can
of
see.
Course.
Yeah, you can see the depth estimation results.
Yes.
Our results can be more accurate at some details. Like
yes, detail. Is it a pedestrian?
Yeah. In some details. Yeah.
I see. So it's like closer to the ground truth, right?
Yeah. The first is the ground truth. It is interpreted for visualization.
Okay. Thank you very much. And I also have a very stupid question. It's on the table above these visualizations. Table 1.
Table 1.
There is one row that is blank. Its accuracy metric is blank. It's Lego 1.
Lego 1.
Yeah, the Lego. There is a method called Lego, right? And in the Lego method,
I can see.
Yeah. Why is there no accuracy metric for this method?
I didn't find the data in his paper about the 3 metrics. Maybe.
Okay, I see. Maybe they didn't want to show their result. Probably. Yeah. Okay, thank you very much.
Probably.
And this is my question. For other attendants, do you have any other questions? Okay, I didn't receive any question. Okay, there is one. Can you see that? The masks generation automated. You design the masks for each occasion, or is it generated automatically?
What?
You can see the chat box. Yes. Are the masks generation automated? So for the masks, do you design them manually or are they generated automatically?
That is designed. Yeah, we designed the mask, but the calculation process is in the training process. When the network is training, we can get the depth, the pose. Then we use the estimated depth and the pose to calculate the mask. That is manual calculating. Yeah.
Oh, I see. Do you need to design different masks for different occasions?
We design the overlap mask and the black mask just for the occurrence condition. But the last mask is to filter the the pixels are have a small error, a large error.
Yes.
When this pixels has a large mix match error, then we filter these pixels.
Yes, I see. So for occlusion conditions, there are not many, right? So you can use a
like
few
this
number
image.
of masks. And for less than mean mask, so this is fully automatic.
Yeah.
Yeah, because it's quite straightforward. Okay, so we have no more minutes. So thank you very much. And
Thank you.
thank you very much. And I will proceed to our next speaker.
Okay.
Mr. Wang Zi. Mr. Wang Zi, are you in the meeting room?
Yeah, I'm here.
Okay, it's great.
I can hear you.
Mr. Wang Zi is a PhD candidate in aerospace science and engineering in National University of Defense Technology, NUDT. His research interests include pose estimation and transfer learning. And today, his presentation topic is monocular pose estimation of rigid objects based on hybrid data. Okay, Mr. Wang Zi, I'll recede and pass the screen to your presentation.
Okay.
And don't forget to vote.
Oh, can you see PPT here?
Yes.
Okay.
Yes, it's quite clear.
Okay. Now I'm begin. Good afternoon, everyone. I'm Wang Zi, coming from National University of Defense Technology in Changsha, China. In the past 1 year, I have done some interesting research about 6DOF object pose estimation. I'm going to give a presentation about this work. Estimating 6DOF object pose from a monocular RGB image is a fundamental and important problem in computer vision and photo geometries, and has gained an increasing attention as it has become an important problem in rapidly evolving technological areas related to autonomous driving, robotic manipulation, and space missions. Building depth sensors may help solving this problem, but such cameras have limitations with respect to frame rate, field of view, and resolution, making them difficult to detect objects in wild environment. As deep information is lost in monocular RGB images, there are several challenging problems in 6DOF object pose estimation. The first challenge including unseen pose and the training dataset and occlusion. The images of 3D objects varies a lot, and as a camera pose changing. If camera pose distributes are not well aligned between training and test dataset, the estimator may show deteriorated performance. When an object is occluded by another, the map from 6DOF pose to an image is broken, leading to a harder task. The second challenge refers to pose ambiguities, which is the result by 6DOF pose and images are not corresponding to one by one. There may be multiple images corresponding to the same pose due to the symmetrical characteristics of the object or occlusion. The third problem is lacking of real trained data, which comes from collecting and annotating images. Images with 6DOF pose are not only time-consuming and labor-intensive, but also require special equipment. Utilizing synthetic images is a promising approach. The last problem is about texture. The images of poorly textured objects contains less information for training, and the images of well-textured objects may vary a lot with lighting condition changing. We have studied the later two problems. The first research is the detection of texture-varied objects. When constructing the training dataset, it is almost unrealistic to collect the images of texture-varied objects. Moreover, it is difficult to obtain real images of some military objects. Therefore, we use a 3D model of the object to generate the texture randomized dataset and train the detector. We choose the squirrel model in about dataset in our experiments. The synthetic images are obtained by rendering the 3D model using Blender. Various render settings are randomized, including camera pose, lighting, texture images, background images, and etc. To learn a stronger detector, we modify the FastRC model in second stage, theory training. The ROI heads are supervised by viewpoint classes. Then, during test, all results predicted by ROI head are treated as the same objects and are proposed using AMS. We 3D printed the 3D model and got several squirrel objects, on which we paint in various colors. We collect the object image in disorganized environment with varying lighting condition. 417 images are collected, and we test our approach with 3 detectors with different structures, including fast assay, SSD, and fever box. Figure 2 illustrates that the performance of 3 detectors increased with the number of unique texture images, which proves the effect. Research from synthetic data. First, which consists of a feature space and a marginal distribution. A task is denoted as T, which consists of a label space and a conditional distribution. Then we introduce the problem setting. A source domain is denoted as DT, DS, and TS, while the target domain is denoted as DT and TT. Usually, the marginal distributions of source and target domain are not equal, which is called domain gap. And we have same feature space and label space input domains. The samples of source domain are well labeled, and the knowledge of the source domain can be learned in a fully supervised way. However, the samples of target domain are not labeled, and the knowledge of the target domain can be learned via transfer learning. Our method is based on adversarial training and step training, where we unified conditional adversarial training and self-training in one loss function. Figure 1 shows the model structure. The model consists of 3 components: the feature structure G, the classifier T, and the conditional domain discriminator D. In a training batch, source images and target images are sent into feature structure G. Then the classifier makes a prediction on both features, where F is the last feature in classifier, and G is the output through softmax. The domain discriminator D is conditioned on the classifier prediction. M is the mapping function that blend F and G. The loss consists of 3 parts, including classification losses for source and target samples, and discriminator loss. Note that the classification loss of target samples is computed using postal labels. The classification loss is cost entropy loss, and the discriminator loss is binary cost entropy loss. The object function is the minimax problem. The discriminator D is used to classify which domain the input features belongs to, while the background G tries to extract domain invariant feature representations to confuse the discriminator, matching the global features across domains. In the loss function, We treat the label for packet symbols as implicit variables. The parameters of network G, T, and D can be learned continuously using SGD. However, the postal labels are discrete. Soon, we optimize the network parameters and postal labels alternatively with alternating two steps. First, step one, fix postal labels YT and minimize the loss with relative to the network parameters. Step two, fix the network parameters and update the postal labels of target symbols. We call one step of one followed by one step of two as a one training round and repeat the two steps for multiple rounds. The quantity of postal labels is essential to model performance, but hard to guarantee. A self-paced learning strategy is adopted in training process. During training, we increase the proportion of postal labels as training round increase. We compare our approach with several state-of-the-art orthograms on three commonly used datasets, including Office 31, Image KFDA, and Office Home. Table 1 shows our results on Office 31. It is desirable that the proposed approach substantially outperforms the most method in 5 tasks and gets state-of-art performance, which reveals that self-training with postal labels have a positive effect on adversarial domain adaptation. On the two hardest tasks, D2A and W2A, our approach gets the highest improvement. Table 2 shows our results on Image KFDA, and we get the best performance on 5 transfer learning tasks, but with a smaller average improvement compared with the result of Office 31. Table 3 shows our results on Office Home. The 4 domains of Office Home have more categories and a great domain gap between each other, leading to harder transfer learning tasks and decreased model performance. Nevertheless, our model significantly outperforms the comparison method on most transfer tasks. We show the influence of the postal label portion on model performance in Table 4. We increase P from 0.2 to 0.7 by a step of 0.1 and conduct 3 random experiments on dataset of Office 31. The average accuracy increased slightly when P is smaller than 0.4. We obtain the best performance at P equal 0.5. We visualize the feature representation of the task A2W in Figure 3 and compare the 3-4 methods, ResNet, DAA, CDA, ADE, and ours. The source and target are well aligned and the categories are discriminated better by ADA, ADE, while the centers are evidently better than by ours. We testify the convergence performance on the 4 approaches, with the test precision on task A2W shown in Figure 4. The proposed method enjoys same fast convergence as CDA-ADE at the 4th training round and get a steady improvement after adding classification supervision with postal labels. There are several work to do in the future. To further explore synthetic images in 6DF object pose estimation, feature level alignment can be utilized. Another important avenue for feature work is explore objects presentation in this task, such as points and contours. The last further work is the use self-supervised techniques in 6DF object pose estimation to obtain a more robust estimator. Oh, my report is finished. Thank you. Is there any questions?
Thank you very much. And the convergence speed and precision is very impressive. I have 2 questions. Okay. The first question is it very common to see the pattern varied objects in the real world?
pattern variant.
You mean texture? Sorry, not pattern.
Yeah, I mean
Texture variant.
texture
So
variant.
is it? Are they common in daily life?
Data line is actually not common, but in military use, some objects can be camouflaged, such as
you mean camouflage, right? So
camouflage.
changing it.
Yes, yeah.
I see.
May,
so another question is for depth sensors, for example, like radar, right?
Radar,
or SAR.
yeah, radar. SAR, yeah.
So they're independent. So their measurements are independent of texture. So why not like using other like sensors or even binocular sensors?
Such sensors can be such sensors in our application. Our application is used in wild environment. Such sensors can be used work very well in indoor environment, and in 6DOF object pose RGBD approaches using RGBD images usually get better performance than approaches only use RGB images. But
of course,
yeah. But this cameras has a limitation on frame rate and the field of view. Usually they only can work at 12 FPS or 10 FPS. Can't some way can't use it in our application.
Yes, but we are not in the. I mean, we're not talking about like domestic applications. So your focus is something. We're not talking about domestic indoor applications, right?
Oh, okay.
Right. So if you're talking about something like military, why not SAR? Why not radar?
Oh yeah, SAR radar is a is a good question. Because they are they show less precision performance.
I agree.
Can you understand?
Yeah. Because they have like a poor resolution compared with like image, right?
Yes.
Okay. I think I can catch your idea now. Thank you very much.
Thank you.
Any other questions? Mr. Zheng Yi, did you have you collected any questions? Okay, so this is very brilliant work with, sorry, there is one. Now from YouTube. Of course.
YouTube, yeah.
Okay, thank you very much and for the impressive work in convergence speed and precision. And let's proceed to our next speaker. Mr. Zhang Yanghao, are you in the meeting room?
Yes, I'm in the meeting room. Can you hear?
Could you increase your voice amplification? Your microphone volume? Your voice is
How about now?
It's very small. It's very small voice to catch. I'm not sure if other attendants can hear you clearly.
Can you hear me right now?
But okay, so could you put the microphone closer? Mr. Zhang Yanghao. Okay, Maybe you're doing some adjustment and cannot like hear me.
I think I will just mute. How about right now?
It's better. It's better. But
yeah.
you can still optimize. You can still optimize a little, you know.
Let me see how to do it. Is it better?
Yes, I think this is acceptable. And
okay.
Okay, thank you. And Mr. Zhang Yanghao is a PhD candidate in Center for Autonomous Systems from University of Technology, Sydney. His current research is related to SLAM in deformable environment. So everything is not rigid now. And his presentation topic is deep learning assisted automatic intraoperative 3D aortic deformation reconstruction, so which is a medical application. And for the audience, please remember to vote if you like this presentation. Scan the QR code. Okay, Mr. Zhang Yanghao. And you can start your presentation.
Okay. Sorry about my computer. Now I've shared my slides. Okay, can you see my slides?
Yes, the slides and voice, both.
Okay, good, cool. Hi everyone, I'm Yan Hao. I'm from the Center for Autonomous Systems, University of Technology, Sydney. I'm a PhD student. It's very happy to have me introduce our recent work, framework for blood vessel 3D deformation reconstruction. So I changed the topic to make it easier to understand because there are a lot of different words for medical field. So currently we have two conference-related papers. One paper is accepted in ICAR 2020, and one paper is accepted in MICAI 2020. Okay, first of all is the background story. So the thing is that current individual interventions rely on 2D observation for 3D patient guidance. But at the same time, 3D preoperative model is available, but it cannot be used directly because the vessel deforms if you put a catheter in the vessel. So the aim of our work is to provide a framework that recovers the vessel's 3D deformation using a preoperative model and two intraoperative X-ray images. And this figure shows the problem description, the input and the output of the framework. So the input is a 3D model and two intraoperative X-ray images. And using these two things, the output is the reconstruction of the intraoperative 3D vessel's deformation. Okay, so the idea of the framework is very straightforward. And to achieve the deformation reconstruction, we need some features from the image. We need 2D to 3D correspondence between features and 3D model. And then we estimate a deformation field to recover deformation. So because the X-ray image is a bit different from the normal image, so we find that using pixels of vessel wall contours is a good way. So we use this contours from the image as the features. And to extract those features, we use a neural network architecture. After training the neural network, this is the result. The second figure is the result from the neural network. We binaries the result, and then the contour can be easily extracted using a more neighborhood tracing method. And then is the 2D to 3D correspondence. So from the model, we project the model onto the image, and also we calculate the boundary of the point cloud projection using the alpha shape method. And from the image, we build a 2D signed distance field. The good thing for signed distance field is that because after building a signed distance field, the distance and the Jacobian can be directly raised from the field, and so there is no need to recalculate the correspondence during the optimization. During the deformation parameter optimization, and building the signed distance field is not is also you can do it in a not very expensive way by using, for example, by using a CUDA implementation. And for the deformation reconstruction, the deformation field is formulated based on an algorithm called embedded deformation graph. So the main idea for the embedded deformation graph is to using a weighted average of local affine transformations. I call it embedded deformation node or ED node to represent the whole deformation. So for the ED node, it is used to represent this the surface mesh, and it is downsampled. If you have a model, you downsample the model vertices and get some positions, and you treat this position as the ED node. And at the same time, you also each ED node also have another two things. One is a fine matrix, and one is the transformation. So I show a figure. So this figure, the green one is the gray color shows the mesh model, or you can just treat it as a 3D point cloud, and those small frames are representing the embedded deformation node. So having this having this A, T, and G, you can the new position of each vertex can be calculated using this equation. But this is the case when you have the parameters of ED node. The thing is that we want to optimize these parameters based on the observation. So, and this can be achieved by optimizing the rotation and transformation of each ED node by minimizing this energy function. So there are three terms. The first term is the rotation term. It is used to make the fine transformation matrix close to a rotation matrix. And the second term is the regularization term. It is used to smooth the deformation, which means that we want the effect of ED node and its neighboring node should be should be almost the same at the overlapping place. And the third term is the observation term, because we want the deformation as close to our observation. Okay, so this is the original algorithm for the embedded deformation node. But for our case, because the X-ray image is only 2D observation, we need to modify the observation term by using a 2D back projection error. So this is our modification, and this new G just means the projection equation, and this D is the distance from the signed distance function. Okay, so this figure shows the main process of the framework. So it can be divided into two parts. One is the preoperative operations. One is the intraoperative operations. For the preoperative operations, a 3D model is extracted from the raw CT scan. And at the same time, we also train the neural network using simulated images and the real X-ray images. And for the intraoperative operations, because we have the model and we have a trained neural network, and a feature can be extracted from the neural network. And after extracting features, we build a signed distance function, and we also have a model. We project the model onto each image frame, and we calculate the correspondence. And then the model is also one of the input of for the algorithm to solve the deformation, and the correspondence is another input. After getting the deformation parameters, we can reconstruct the deformation. Okay, So this framework is validated by a real phantom experiment. So for the experiments, we deform the phantom 3 times, and the ground truth is obtained from CP. And at the same time, the fluoroscopic images for 4 different directions are also obtained. Okay, so here is one of the results. The first figure shows the input model colored by gray color and the ground truth. And the following 2 figures shows the 3D result. And then is the error. And the last 2 figures shows the projection, shows the 2D projection. The blue color shows the projection of the input model, which is the gray color. And the red color shows the result, projection of the result. Okay, that's all for my presentation. Thanks for listening. If you have any questions, please do reach out.
Thank you very much. I have one question.
Yep.
I think maybe I missed something, but I'm curious about how to establish the correspondence, I mean the node correspondence, like between 2 images, or between the 2D image to your 3D model.
Yes.
So you,
the thing is,
you have many nodes, right? Yeah.
Let me see. Okay, so the thing is that because here we use the sign-based function.
I can understand this like slide, but there is one slide related with optimization. You're trying to minimize the error. Can you show that slide? Yes, the E rotation, the previous one. The previous one.
Yeah. The previous one. Okay.
Previous. Yes. So you have the rotational error, right? Registration error and OBS. Observation error, right?
Yes.
So to get these errors, you must have the node correspondence.
Oh yes. The thing is that the observation. So the correspondence is only for the observation term. Okay. So the first 2 term is kind of a prior knowledge for this is kind of a prior knowledge for the algorithm. So which means that,
I see.
Yeah. So the correspondence is based on so you calculate the correspondence from a model vertex and your image. Yeah. And because we use the
then you
sign-based
can
function,
optimize.
yeah, then we can optimize. And the good thing for sign-based function is that yes, there is no how can I say this?
Okay.
Yeah. Then you.
And thank you. And my second question is, are you the first researcher that like trying to map a 2D image to a 3D like model for
no.
I think this is for in situ like surgery guidance, right?
Yeah. The thing is that we find some related work similar. The target is a bit similar, but usually this work use the center line. They find the correspondence of the center line instead of or they recover the deformation of the center line instead of the whole shape of the vessel. And we find we find a very similar work, but they need additional information. They need the position of the inserted cater.
I see. So that's why you didn't have the comparison with other methods, right? Because it needs more information. Okay, thank you. And there is another question collected from YouTube. The question is, how do you obtain the training data set? And what's the size of the training data set?
For the training data set, because we have 3. One of the because we have 3 data sets. one of the data sets
Okay.
is used for training.
So this method like can be successfully applied even with a very small data set.
No. The thing is that the image that we use for training is
Yes.
Yes, it is a good question. The image we
Yeah.
use for training, because when we scan the phantom, when we doing the CT, we
Yes.
use a C-arm. So the good thing
So
for
you
C-arm
have
is that
ground truth.
yeah, we have the ground truth. We have the data for CT. We can also have a video that is very similar as the X-ray image, but from different viewing directions.
Yes.
Yes, and we use, because this is a video, there are many images, and we use the images from the video to train the neural network.
Oh, so, but still this like data set is very small, but it has very good performance. So
No,
this is
it's not that small. It's because we train the network. I mean, firstly we simulate around 600 images to train the neural network, and then we use around 200 images to refine it.
Yes. So this is moderate. It's not large, right?
Yeah.
Okay. Thank you very much. And any other questions? From Bilibili or YouTube? Okay, thank you very much. And I'm going to close this session, and let's have a lunch break at your own cafeteria. And during lunchtime, there is another program on visionary revolution, 3D sensing in our everyday life by Dr. Zhi Chen, and also our sponsors publicity. And thank you very much, and see you afternoon.